This week, we're asking you, the listener, to go fill out a survey for our advertisers. It will help us get the best ads for our listeners, so more of stuff that appeals to you and less of stuff that you really, really want to fast forward through. I will also be reading these results, so I do want to know if you're working in sciences, if you're listening in the car, on the train, in the gym, in the lab. You get it. So please go to podsurvey.com/sciencemag, that's science-mag this time, and take a quick anonymous survey that will help us get to know you a little better. Plus, once you've completed the survey, you can choose to enter for a chance to win a $100 Amazon gift card. Terms and conditions apply. Again, that's podsurvey.com/sciencemag, SCIENCE-MAG. Thank you for your help. Welcome to the Science Podcast for February 22nd, 2019. I'm Sarah Crespi. In this week's show, I talk with Lizzie Wade about monitoring a building's health in real time. Can sensors tell us if a building is structurally sound after an earthquake? And Meagan Cantwell talks to Svetlana Botsyun about a new estimate for the height of the Tibetan Plateau 40 million years ago. It turns out it was about 1,500 meters shorter than we thought. What does it mean that researchers were wrong about its height, and what else might we need to recalculate? Now we have Lizzie Wade, a contributing correspondent for Science. She writes this week about monitoring the structural integrity of buildings kind of in real time, taking a look at how they're dealing with vibrations and how they fared after an earthquake. Hi, Lizzie.
Hi, Sarah.
I wanted to start with, the fact that you live in Mexico City and there was a really big earthquake there recently. And this is something that's very important to, say, people who live next to a building that collapsed. They want to know, did my building just make it through by the skin of its teeth, or is it okay now? And you visited a school that did not make it through. Can you talk about what that was like?
Sure. Yeah, I think people who haven't been in an earthquake where buildings have collapsed don't really know how much the uncertainty can weigh on you afterwards. I visited a school in the state of Morelos in Mexico, which is very close to the epicenter of the earthquake that happened on September 19th, 2017, which was the last really big one that we had here in Mexico. Most of the school is one-story buildings, but there's one that's a two-story building, kind of a classic big staircase leading up to the second floor landing that lets you into various classrooms on the second floor. And during the earthquake, one of the columns holding up that landing cracked and the landing tipped over pretty precariously, and all the kids were inside. It was very scary, and everyone got out okay, and the building was still stable enough to be repaired. They repaired the column and repaired the landing, and it was then fine. But the principal told me that the kids were scared for months to go back up to the second floor classrooms.
Right. And I know that there are earthquake proofing techniques that can go into building, but those aren't always available. They're not always enforced. What we're going to talk about today is monitoring your building's health using some kind of sensor. What would the sensor be listening for or looking for?
The basis of these sensors are accelerometers, which basically measure the movement of a point in three-dimensional space over time.
I'm waving my phone around right now, and my phone knows it.
Exactly. Yeah, so accelerometers are in lots of things. They're the basis of national seismic networks that countries deploy around their seismically active regions to measure the magnitude of earthquakes and things like that. They're also in your phone, in your car, in video game controllers. Accelerometers have gone through this huge revolution recently. Previously, to get a really sensitive accelerometer, you needed to spend a lot of money.
Yeah.
And now you can get really, really affordable accelerometers that are quite sensitive.
I was surprised to learn that a very fancy, I guess you would say, very expensive skyscrapers do already have sensors on them that detect shakes or wind or that kind of thing.
Yeah, for a long time, I think in places like California and Japan, especially during construction of skyscrapers and bridges, they put in these expensive accelerometers and sensor networks. And basically what the accelerometers are doing is measuring continuously the vibration of buildings. Buildings can vibrate from a lot of things. It can vibrate from a big earthquake and can vibrate from a garbage truck driving by. So if you can measure the continuous vibration of a building, you can know something about its properties and then kind of judge how those properties may have changed after a big earthquake.
Right. Well, let's talk a little bit about the kind of analysis that you need to do. So say you have a sensor. We're not talking about the big fancy skyscrapers anymore. We're just talking about a sensor in your school. Is it measuring all the time what the, any vibrations hitting it and adding those up through time? Or is it just saying, oh, something's changed about the building, and you may need to do an inspection?
Yeah, it's more the second one, although it measures all vibrations continuously, which is also newly possible thanks to cloud computing and how cheap processing power and data storage has become recently, because obviously if you're measuring every second of a building's vibration, you need somewhere to put that data, which also was a big challenge. So it measures the vibrations continuously, and that can tell you things like the resonant frequency of the building, but what the affordable networks really focus on, because this is one of the best defined parameters in terms of like translating it to what it means in the real world, is a thing called interstory drift, which is basically how much the different levels, different floors of a building jerk out of alignment with a big shaking event like an earthquake. I mean, it could happen theoretically with any kind of shaking event, but the ones that we're worried about are big earthquakes.
Right. And you mean with respect to each other during the event, or once the event is over, how far out of alignment they are?
I think it can be either, although I'm not totally sure. I think it's like sort of how far they've jerked out of alignment. And then sometimes I imagine they can come back into alignment, but knowing that it passed this threshold. Every building has a threshold beyond which the potential for damage becomes really high. It's important to know, even if the building looks fine, and if you took a measuring stick and like measured how far out of alignment the floors are after the shaking stopped, it could still have passed the threshold during the shaking. And so, so that's important to know.
You did mention that there is some kind of value that you want to compare against, but that is a bit of a tricky part for this. Like, where do the data come from that tell you this is a healthy building, this is the threshold, now this is a dangerous or sick building?
Yeah.
Can you talk a little bit about where that data comes from?
Ideally, you would do it based on structural models of individual buildings. My apartment building, if I got one of these really expensive sensors installed, we'd go to public records or go to the architect of my building and get the exact blueprints and make a computer model based on my building. And then that would be a pretty stable and firm comparison to like the real world. That is really expensive, and sort of the point of this technology, and the reason, it can be going in public schools in Morelos, Mexico, is that it's supposed to be cheap. So what these companies are doing, and there's a company in Mexico that I visited with, there's another company in Taiwan, and there are others throughout the world. They basically use standard blueprints for various very typical building designs throughout the years. So the school in Morelos, for example, like was a really classic 2-story school design. Like, these things are all over Mexico. They felt pretty confident. The company called Grio felt pretty confident that with the blueprints that they had, they would have a good idea of how this building should move. To really like have more certainty, you do it based on a individualized blueprint of that building.
Okay. Back to the school for a second. There was a discussion, or there was a mention in your story that they were going to have a go, no-go light. So it would reassure the students, but also it's basically letting you know the health of your building whenever you walk by it?
Yeah, so there's a stoplight now. It's like a thin cylindrical tube with a green, orange, and red light, like a traffic light. And it is normally off, although every day in the morning it ticks through the lights if everything is working smoothly. That's sort of the sign that it's okay. And then after an earthquake, what will happen is if the building has not passed the threshold of interstory drift and other signs of damage, the green light will go on for 5 minutes, and that will say, okay, this building's very, very, very likely safe to return to. And then if there is some damage detected, either the orange light or the red light will go on. And red is like definitely damaged, do not go back in. And orange is probably damaged, maybe damaged, still don't go back in.
Right.
And that's because there's always going to be some uncertainty inherent in these systems, although, there is also uncertainty inherent in the inspections that engineers do. One of the ideas is that if you had sort of a critical mass of these stoplights and sensors in the chaotic hours after a big earthquake, the engineers who go around and inspect buildings would have some guidance. It's like, okay, red light, do not go into this building. This is really important that we see. Orange light, come here right now. We're not sure. green light, we can wait a little while to see if they're okay. That's a really big priority, especially for the companies who are trying to deploy this.
I have here on my question list, can this give you a warning so that you have advance notice and you can run out?
The sensors that I'm talking about here don't give you earthquake early warning, but actually something that's not in my story is that many of these companies also work on earthquake early warning, because the kind of sensors you need to detect these very early signs of shaking are also plummeting in cost and can be deployed in large numbers.
It sounds like there's companies already selling these products, figuring out how to install them in schools. What further refinements? What's the next step in the science?
There's other things you can measure in a building other than inner-story drift. Like I mentioned, resonant frequency. Resonant frequency, the classic example is a tuning fork. You hit it and it always resonates at the same pitch, because that's its resonant frequency. Everything has resonant frequencies, including buildings. You can see with these sensors sort of changes over time in resonant frequency, both before and after an earthquake, but also buildings that have been monitored for a long time seem to just randomly change their resonant frequency. Figuring out how that corresponds or doesn't to actual damage in a building, that's an unanswered question and potentially interesting. Like, you can get a lot of information out of these sensors. Scientists don't actually know what to do with all of it yet. So that's kind of interesting. And also in the future, if you had even better sensors, more of them, ones that were more tailored to individual buildings, it might even be able to tell you eventually, not just crude red-green light dichotomy kind of thing. It might be able to tell you this is where the damage is likely in your building, which would be even more guidance for civil engineers. That would take a lot more data. Like, it would have to be deployed on a massive scale with massive investment. But that's something that scientists could theoretically do in the future.
Wow, really interesting, Lizzie. And I just have to mention that when I read Interstory Drift, I thought of all the writers who work here and what happens to them between the stories that they're working on.
I'll also think about that now. What a great metaphor.
Okay, Lizzie, thank you so much.
Thank you.
Lizzie Wade is a contributing correspondent for Science. You can find a link to her story at sciencemag.org/podcast. Stay tuned for Meagan Cantwell's interview with Svetlana Botsyun about measuring the height of the Tibetan Plateau 40 million years ago. Stay tuned for Meagan Cantwell's interview with Svetlana Botsyun about measuring the height of the Tibetan Plateau 40 million years ago.
The Tibetan Plateau is a vastly elevated area in Central and East Asia, with an average elevation of 4,500 meters. This mountainous region has some mystery surrounding it, though. Specifically, when did it reach its towering height? I'm Meagan Cantwell, and I'm with Svetlana Botsyun to talk about how they determined just how high the Tibetan Plateau was over 40 million years ago. Hi, Svetlana. How are you?
Hey, I'm good.
First, could you talk a little bit about the theory behind how the Tibetan Plateau initially formed?
The Tibetan Plateau was formed during the collision between India and Asia plates about 55 million years ago. The plates came together and they collided, and the plateau started to uplift. But actual timing of uplift is unknown. There are still a lot of discussion on the height of the Tibetan Plateau.
Your field of research is called paleoaltimetry, and that's the study of past elevation of land surfaces like mountains. And it's pretty hard to quantify, but your team did arrive at an estimate of how high the Tibetan Plateau was 40 million years ago during the Eocene. Could you talk a little bit about your methods for how you determine this estimate?
So we go to mountains, we measure carbonates, and we use theoretically established relationship between elevation and oxygen isotopes in precipitation, and can guess what was paleoelevation. But in our approach, we suggest to do another method. We suggest using climate models, because oxygen in precipitation is influenced not only by elevation itself, but also by paleoclimate. And with a general circulation model called LMDZ, it's a French model, and it can produce a global climate. And numerical climate model, we have access to both, to paleoelevation and to paleoclimate.
Just looking at the isotopes within these carbonates isn't going to tell you what the elevation was, because there's other factors in play, like the climate that you have to take into account?
Without knowledge about paleoclimate, without running a special climate models, we actually can misinterpret this record. So that's why we're suggesting running climate models.
So how do you know what the climate was like this far in the past?
It's difficult to know. We can try to apply several boundary conditions. For example, we know that concentration of greenhouse gases in the Eocene was different from today. We also know that paleogeography in the Eocene was different. For example, we had this Parateti Sea to the north of Tibetan Plateau that has a potential influence on climate in the region. So we apply these boundary conditions and we ran a global general circulation model that could predict climate based on those boundary conditions. And a cool thing in our model that we have implementation of stable oxygen isotopes directly. So we simulate in a model stable oxygen isotopes together with a climate change. So we have both. We have stable oxygen isotopes and climate.
How does the Tibetan Plateau currently impact the climate around the area?
It's a main driver for the monsoon over Asia and India. It also impacts global climate because it's have a huge impact on global atmospheric circulation. When the plateau is not that high, it's possible that the monsoon circulation is different from today. So that's why it's so important to know the elevation.
Based on taking into account the climate during the Eocene, what was your team's estimate for how high the Tibetan Plateau was 40 million years ago?
It was about 3 kilometers high. So today it's about 4.5 kilometers high. This contradicts previous studies, which concluded that probably in the Eocene, Tibet was at the same elevation as today.
What kind of impact would that have had on the climate?
In general circulation model, it's kind of the same. So we have a monsoon. We able to simulate Eocene monsoon in the region. And we also have westerlies. Westerlies is winds that coming from west to northern part of the Tibetan Plateau and Central Asia. We do simulate this global climate features. But precipitation amount itself was different. And it was also warmer because of this greenhouse gases concentration in the atmosphere. It's warmer climate with more convection, different amount precipitation. So in the southern part, it was more likely more precipitation, but to the northern part of Tibetan Plateau and Central Asia, it was dry.
And that difference in climate probably changes the types of flora and fauna that could survive in the areas. And what's interesting is that fossil evidence in the past has supported a lower Tibetan Plateau during the Eocene.
Our interpretation of stable oxygen isotopics data are really supported by paleobotanic evidences.
If the Tibetan Plateau was not at its current height 40 million years ago, that must mean there was some kind of uplift event in between 40 million years ago and now. Does your study say anything about when the additional uplift event could have occurred and what might have caused it?
With our study, we can't tell what exact reason of this elevation. It's a job of geodynamicists.
Right. Lots of people have to work together to solve that.
Exactly.
I'm curious what the uncertainties and limitations to your modeling approach are.
We have uncertainties linked with our modeling, of course, because we put into a model several boundary conditions. For example, estimation of greenhouse gases in the atmosphere. It's within best for today estimation of CO2. Another uncertainty linked is using Eocene paleogeography. Based on other methods, such as paleomagnetic studies, we could tell where was position of India, where was the Parateti Sea at that time. So we used the best for present-day existing paleogeography and put it into a model. But we are aware that it could be that paleogeography was different for the Eocene.
There's so many other reconstructions that have to be refined in order to get a good paleoaltimetry estimate. So since you determined that you kind of need to have other factors taken into account in order to determine the elevation, how do you think this will change how things are studied within your field?
I'm pretty sure that the results of our research would have quite an important impact on diverse communities of geoscientists. This method could be applied in any region of the world, let's say in the Andes, Cascadias, or the Alps. Second, we have shown that the elevation of the Tibet was probably not that high in the Eocene. This is important, for example, for a geodynamical community, for understanding the timing of geodynamical events over the region.
Svetlana Botsyun is a postdoctoral researcher at the Tübingen University in Germany. She also conducted this research in the Laboratory of Climate and Environment in Paris, France. You can find a link to her research at sciencemag.org/podcasts.
And that concludes this edition of the Science Podcast. If you have any comments or suggestions for the show, write to us at sciencepodcast@aaas.org. Yeah, and please do let me know where you listen to the podcast. I'm pretty sure the survey isn't actually going to ask that question. So write into us and tell us where you're listening, be it lab, car, train, what have you. You can subscribe to the show anywhere you get your podcasts, or you can listen on the Science website. That's sciencemag.org/podcast. To place an ad on the podcast, contact midroll.com. The show was produced by Sarah Crespi and Meagan Cantwell and edited by Podigy. Jeffrey Cook composed the music. On behalf of Science Magazine and its publisher, AAAS, thanks for joining us.